So good morning. As a first topic, I will finish the topics of fundamental fields or generators, of rotations and translations on E3. So this already was, and so this is now important that I didn't finish this translation, and I will not do it. I will just show that from where we come, that in some formalism with bigger matrices, which is convenient, we know that there is an action of this structure so here we have both rotation and here is a column, and this means that it is actually affine transformation but with special matrix, which is rotation matrix. So this pair or this matrix actually realizes action of Euclidean group on E3. Yes, these matrices are from Euclidean group if A is from SO3. And I computed what are generators at the very end of the last lecture. Computed generators psi for the basis Li. Li is a basis of small SO3, so Lie algebra. It is given by, they are antisymmetric matrices, Li jk equal minus epsilon ijk. And after some computation, we came to the result that the generators can be written like R cross nabla I. Yes, so it is explicitly minus epsilon ijk xj derivative with respect to k. So this is a generator, the vector field on this E3, on these vectors R, for the rotational part. And one can compute similarly, it is easier, and I will not do it here, that there is a basis of this Lie algebra. Lie algebra of this group is a span of Li 0, 0, 0 and 0 EI 0, 0. Here the Lie algebra is given by antisymmetric matrices and some columns and 0, 0 here. So this antisymmetric matrix can be decomposed with respect to this part of the basis and this small x with this part. And what is this part? For example, E2 is 0, 1, 0. So E1 is 1 at the first place and so on. So natural basis for columns. And here is more or less natural basis for antisymmetric matrices. So altogether, this element and this element is a basis. In E3. it is Lie algebra of E3, which is Euclidean group that is group of isometries of this E3. This difference, this E3 in the bracket and E3 as an upper index. This is a space and this is a group, isometries of this space. And if you now compute the vector field EI, so here we have a vector field associated with this part of the basis, and the rest of all fundamental fields is a span of these three vector fields, which are associated with the rest of the basis for translations. And if you do the computation, it is easy, especially in this formalism. You come to the result that it is derivative with respect to I, with minus. These minuses, by the way, are not important here. It means only that whether you do it by G or G minus 1 element in general. What is important is this outside of this minus. So now this and this are altogether 6 vector fields, 3 for translations and 3 for rotations. And what is interesting that, of course, this is again this is minus R cross nabla I, and of course this is minus just nabla I, yes? And I intentionally write it in this way in order to make the similarity as big as possible with something from quantum mechanics. And this something from quantum mechanics is that there is an operator in quantum mechanics, which is something times this R cross nabla, some constant, and operator P, which is again something times this nabla. And here is some multiple of H, of Planck constant, which is not important in our geometrical thinking, but this part is important. So they are operators denoted by heads in quantum mechanics. Now we see that these two operators, which are essential for standard quantum mechanics, have very, very easy interpretation in our thinking, that these are actually 3 operators and 3 operators, and these 3 operators altogether generate rotation, and those operators generate translations. Now, of what? Of quantum system described by wave function psi from quantum mechanics. That these operators are applied on some psi r with t, and then they produce rotations and translations. And it is studied in detail in one chapter of every book on quantum mechanics, including the green book, which is the Bible for you, as far as I understand. There is a chapter which is called rotations and translations and something like that. Yes, and it is in the second half of the book, probably, that it is in the summer semester. Now is winter semester, hopefully. Yes, and so perhaps you just wait for it in quantum mechanics, but in some winter semester there will be a special chapter and special lectures here on these topics, that how rotations and translations in more rotations, how they act, and how some facts come from it. There is some representation of group, of rotation group. There are some functions YLM, theta, phi, and so on. Some business around this. So just I point to this fact that we came to similar operators or the same operators modulo this constant from some other point, from geometry, that what are generators as a vector fields, as fundamental fields, generators of some representation of rotation and translation group on functions. And these functions will become wave functions in quantum mechanics in particular, and it is then no surprise that the same operators will be there. Yes, because they have to be there, because they generate rotations and translations. So I don't want to elaborate more on these topics because it will be done. Just remember that when you come in quantum mechanics to these problematics, that it is a good idea to find as much connection to our lecture here as possible, to understand it from both sides, so to speak. Yes. Okay. So by these facts, I finish this week when fundamental fields, not completely, when just fundamental fields, and there is still one point which we didn't do from this week. It is quite short and quite interesting, that there is a special representation of the type which we studied. So what is the type of representations we studied? Remember that we studied representation rho g on psi at m is psi at r g m, or psi at m g. So if we have a manifold or a set with right action of group G, we can study functions on this manifold. The functions give us a vector space, functions on this M. And in this vector space, that means on psi's, representation is defined by this formula, and we studied it, and from the derived representation become these fundamental fields and so on. Now there is a question that how to find, if we want to use this method of finding representation of our group, we need this object, some manifold on which we have right action of our group. So if there is no better idea, now the information is that there is always an interesting M with RG, that M equals G and RG equals right translation. So this choice of a manifold on which group acts is always available. Is that choose as your manifold directly this group, and there are three right actions. We studied it, that left translation somehow changed to the right by the trick G to -1. There is conjugation, and there is directly right translation. So for this right translation, there is some reason why it is so. It is most important or interesting. And now for this material, this idea is that this row, this particular row for this case, is called that it is a regular representation. This is the name of this representation. or better, right regular. There exists also left regular. Left regular is with this left action somehow changed to right one. But we now use directly this right translation. So this representation is then called regular representation. So regular representation for group G, for group element, I will put it here maybe, acting on psi, which is now a function on the group. Yes, because in general it is a function on M, but now we have M as our group, so this is a function on G. This doesn't mean that G factorial, but this is an important notion, that function on G. So this at a point on G group, which is some K, is psi at Kg, which is, this is a product, yes? K is from group, G is from group, it is a product. So this is the right translation, explicitly. This is definition, yes? This is definition of this representation, but it is just a special case of the more general class of representations for the choice that choose this M equal to G and R as a right translation. Now it turns out that this particular representation of this type is quite important in many respects, and I will show just one interesting case why it is important. That consider any or application of this, yes? That consider any irreducible finite dimensional representation rho of G, of this G which is here as M. So it happens in some vector space in some V. Yes. There is a basis here, some EA, and it acts by some matrices with respect to the basis. So we have irreducible finite dimensional representation, so here are the matrices of this representation with respect to some basis. So it is rho G 1, 1, rho G 1 n, here rho G n 1, and rho G n n, and dots. Here is the matrix explicitly. And now, what are these matrix elements? We can think that, for example, this one is what? It is a number associated for any G. So it is nothing but a function on G. Yes, this is important. This is a function of G. This is another function of G. Another function of G. So all matrix elements can be regarded as functions on G. So they are from this space where regular representation acts. Here, that means here, where is it? This guy comes to be F on G. This is the vector space of functions on G. Or manifold, if it is Lie group, smooth functions of G. So these matrix elements can be treated, this is a number, but without this G. Yes, it is from functions on G. So we can act on them by regular representation, because regular representation acts on function of G. And there are functions of G, so why not? And what is quite interesting that if we choose any row of this matrix, so this row, so we introduce what is row, that this index is fixed because it is the first one, and A is, here is A equal 1 and A equal n for some B. So row G BA, we will call that there are some functions which are here. It is a function, eighth function. Yes, that for fixed B, fixed row of the matrix, we introduce these elements in the row like separate functions. And this function, we can now consider span of these functions. It is some linear space, which is subspace of this infinite dimensional space. This is infinite dimensional space. And now we consider subspace given by just this row of the matrix, any row, yes? And now what is interesting, that this subspace is invariant with respect to representation row, regular, this representation. So let's compute that regular representation of G acting on psi A. What we get? This in some K. So by definition, it is what? It is this psi A computed on Kg. Now, remember what is psi A? It is rho Kg BA. By definition, what is just psi? But now it is important that this is matrix of representation and there is a product inside. So it is rho K B C and rho G C A. Because rho is a representation, so it is a homomorphism. Now, with fixed B here, it is psi C on K. Because here is B, yes? So, it is what? It is rho G CA psi C evaluated at K. So K here, K there, we can write it without this K. Regular representation when acts for element G on psi A, what we obtain is rho G acting on psi, or rho G matrix element. I rename CC to BB, BA psi B. Yes, this is the result. And now it is to be compared with this result. And is it something interesting in this? on these two results, that here is any finite dimensional irreducible representation in some vector space. Here are matrices of this representation. Now we computed something. We took several functions on group, and we noticed that regular representation, when acts on these functions, we obtain this result. What is interesting on that? Do you see something, some similarity between these two formulas? Yes, these psi's seem to be the basis of some representation. Okay, this is the first fact. And then, what representation? What is important also in these two formulas? You are right. This is a good observation. That from this formula we already see that there is an invariant subspace spanned by these psi's. But we see also something else also. That what are these matrices there? They are the same matrices, yes? So what does it mean if you have some representation, if you have two representations and in some basis you have the same matrices of the representation? What does it mean? What is the property of these two representations? They are equivalent. So we see that not only this subspace is invariant, so there is some sub-representation of regular group, which is finite dimensional there, but it is equivalent to this given finite dimensional representation. And it happens so many times. What is the dimension of the matrix? Yes, because here is one representation equivalent to this given one. Here there's the second, here is the third, and so on. So if the dimension of the representation is some n, there are n pieces of equivalent subspaces or invariant subspaces in Fg, in the space of functions on G, on which equivalent representations work with any given irreducible representation. So we see that if we want to study all irreducible representation of our group, which is a quite interesting subject also for physics, we can just study the regular representation. Well, it is infinite dimensional, but inside this regular, which is infinite dimensional, you have also all finite dimensional as a sub-representations. Yes? And not only once, but several times even. So this is the interesting fact about one interesting fact about this regular representation, that all finite dimensional irreducible representations can be treated as sub-representations of this representation, of this regular one. Yes? So regular one is, at least from this point of view, very, very interesting. For example, I wrote somewhere this function. These functions, y's, lm, theta phi, usually they are treated as functions on a sphere, but they also can be treated as functions on the group SO3. On the group SO3, maybe you remember that there are some Euler angles. We know it from theoretical mechanics. And what are Euler angles? They are generalized coordinates for the rotating body. Yes? But that means that they are coordinates on the group SO3, because what produces rotations? Group SO3. So we can treat Euler coordinates as a coordinates on the group SO3. We can interpret it in this way. So if you see some function of these three variables, you can interpret it that this is some function on the group SO3. And if psi is not there, it is still a function on SO3 which has some special property, that it is somehow invariant with respect to something. Yes? So also these functions can be treated as functions on SO3 with some special property. And also maybe you remember that there is something like dj, you cannot remember, now I realized. Do you know this function? Did you meet it somewhere in quantum mechanics, I mean? So in the summer semester, in the chapter rotations and so on, you will see both this and this, but maybe this you already saw. Did you do already the hydrogen atom? So in hydrogen atom and similar cases, this is already known, but this will come in summer semester in the chapter rotations and I don't know what. Yes. So, and you see that they are functions of all three angles, Euler angles. So they can be treated as functions on the group SO3. So it is somehow connected with regular representation. Yes. Okay. So this is the end of this week. Where those actions of and representations of this type were studied, connected with concepts like fundamental fields and generators as differential operators, that as vector fields. And now we go to next week. But I will tell also something which is not directly there, but it is useful for understanding the next week. And I will also introduce several concepts which could be introduced sooner, but never mind. It can be also introduced now. That, for example, several definitions. What is it? So first, what is a G-space? G-space is this MRG or MLG. So what is it? It is some space, this is this M, which is meant actually that some set or manifold or vector space, or so the word space means this M. And what is G-space? It is a space, so some set, where some group acts. Yes, this group acts. So this is some set, but not empty set, but a set on which group acts. So you have defined either this or this. This is, so we for some time already do study these G spaces. Yes, these M's with representation. Now, the actions, there are several special interesting actions. One of them is so-called free action, and the second is transitive. I will start with the transitive one. What is transitive action? By definition, there are definitions, that concepts which are defined somehow. Which action is transitive? Transitive action is such that your M is the only orbit of the action. That usually, typically, we have some M here, and this is orbit. So, by action, you can come from this M to all these points, but never to this point, because this is another orbit. You can move only along orbits when you have action of the group. So typically there are several orbits on your M. We computed it. You remember that, for example, GL and R acts on Rn, on columns, and there are two orbits. 0 point, and everything else. SON acts on this Rn. And there are infinite number of orbits which are spheres. Do you remember this? That we computed it, and we saw that typically our M decomposes to orbits, and there are typically several orbits. But sometimes it happens that your M is just one orbit. So this action, which is not like that, but which has just one orbit, M is orbit of any point on M. Because you remember that orbit is defined by any point sitting on this, and now, because whole M is just one orbit, it is generated, the whole M is generated from any of its points. So, here is some M, and you can go to any M primed here by some G. So this is called transitive action. And this G space on which we have transitive action is called homogeneous space. So homogeneous space is a special case of G space where you can connect all points by group elements. Yes? So it can be said differently that there is just one orbit inside. So from this definition we see that if you restrict your action to one orbit, so here was M, but now define this to be some M tilde, just one orbit, so it is now homogeneous space. Each orbit is homogeneous space by definition. Because you can connect 2 points. So when action is restricted to one particular orbit, this particular orbit becomes homogeneous space and the action becomes transitive. But on the total M, from the very beginning, it is not transitive and it is not homogeneous space. Study of homogeneous spaces is important because actually we see that general G spaces are some unions of homogeneous spaces, of these orbits. Yes? So when you study homogeneous spaces in its own beauty, then you learn something about, in a sense, about any G space, that G space is some union of homogeneous spaces. So these are concepts that what is G space, general one, and in particular for transitive action, it is homogeneous space. We will study a little bit homogeneous spaces. Yes?
Does every point on a G space have to be on some orbit?
Yes, yes. The orbit is by definition all points to which you can come from this M. So each M sits at some orbit from the definition. Yes. But you don't know whether this orbit is the full space or just some part of the space. You have to compute it. Now, the concept of free action. It is free action. It is the simplest action, actually. From the structure of this action that stabilizer of any M so here is our M, say LG. Take any M, compute stabilizer for any M. This M may not be homogeneous space. They can be several orbits, yes, in principle. Take any M and compute stabilizer of this M. So stabilizer, we know that is a subgroup of G, always. And what is the smallest subgroup of G and the biggest subgroup of G? From the definition of what is subgroup. They are called, both of them are called trivial subgroups. So what are trivial subgroups? The smallest one and the biggest one. All G and it is the biggest and the smallest. So, sorry? Just unit element. Okay, so there are some boundaries that all subgroups are between the smallest, just unit element, and the biggest, which is the whole group. And free action is such one that this is the smallest one, just E. Yes? So GM is unit element and nothing more. The smallest subgroup. Now, this is definition. We can have now some example. Non-trivial. It means that non-trivial in the content, not non-trivial that huge computation. That example, notice that there are two E's, but here will be example, and here is something EV, some set. EV or EL, maybe EL, are all bases in vector space L. So we have a finite dimensional vector space, and this is the set of all frames or all bases. So what is there? Some E1, En bases in M, in L. I will call it EA for A equal 1 to N, or extremely shortly E. So E is from this. A set of all possible bases in your vector space, n-dimensional vector space. Now we can scramble bases to construct new bases. We know that we can go from a given basis to other bases called primed. And the claim is that this is just right action of some matrices, as we see, on E, A. So in order to get primed EA, you scramble it with some matrix. From definition, in order that the new basis is also basis, when old basis was basis, this matrix should be non-singular. And non-singular means that it is from G, L, and R. So the claim is that this procedure, that choosing of new bases, can be treated as right action of GL and R on the set of all bases. Notice that this can be written in this way, like matrices. But it is the old one, and here is A. Yes. If you have a look how indices are here, this is the first one, this is the second one, then the matrix multiplication gives you new bases from this formula. This is the best way how to compute these bases. If you have two bases and you want to find the change of basis matrix, then write here new basis, old basis, and find what matrix should be applied from the right. because this is the definition in indices. And then, so we can shortly write it in this way. And now it is meant as matrices. This is row matrix, this is row matrix, and this is this matrix A here. Yes. And now it is clear that if we go from E to E prime by A, and from E prime to E double prime by B, that what happens? E double primed is E primed B, but E primed is E A B, which is E A B. So we see that it is right. So the claim is that it is right action. Once again, it is EA. Yes. Compute AB from this formula, and you will see that it is RB, RA. That first A and then B. Here you see that first A. Yes. Okay. So we have right action of GL and R on this set. And now the question is whether it is transitive and whether it is free. So it is more or less question to be a little bit, to think a little bit, not too much compute. That the question is it transitive? That means if you have first basis arbitrary and second basis arbitrary, is there some matrix which connects these two bases? Of course, yes, because this is the main work of transition matrix going from one basis to other basis. It is for each two bases you have a transition matrix, so that means that all two bases can be connected by action of this group. Yes. Otherwise, there were some bases for which you cannot come from some fixed basis. But from any fixed basis, you can come to any other basis, always. So it is transitive. And the question is now, is it free? That if you have the condition that you have fixed basis, and you apply GL and R element on it, and you want that it still is the same basis. So if you have no primes here, just EE, and find that what A's produce this work. For example, here, now the question is this one, and this is the question mark. Yes? If here is A, first basis, which is any, here the same, this is important, and here any matrix A which produces the work. What is this any? So we want to get E1, but you get it by multiplication by two row and column. So the only possibility that here is 1 and here is 0, 0, and so on, and you can come to conclusion that this should be unit matrix. Yes. So A is unit matrix. But this equation is an equation for finding this subgroup. Yes, it is finding of or trial to find this stabilizer of this action. So we see that stabilizer is just given by the unit matrix here. So the conclusion is that this right action is free and transitive. So both free and transitive. So it is quite interesting action, and by the way, very important action. So, because it is transitive, this is a homogeneous space for the group G, L, and R. It is not only G, L, and R space. From the very beginning, from computation that, yes, this is right action, we see that this is G, L, and R space. Yes, that group G, L, and R acts there. But now, from the further computations, we see that not only it is a G, L, and R space, but it is a homogeneous space for G and L, R. And in addition, the action is free. It is not connected with the fact that it is homogeneous space. Very interesting differential geometry is based on this. There exists something called frame bundle, which is in detail discussed on the lecture Gauge Fields and Connections. And so it is not compulsory course in the summer semester of next year for you. So you need first to finish this lecture, then to finish Mathematical Physics 2, and then there are 2 lectures, small, and one of them on Gauge Fields and Connections uses something called the frame bundle, and it is something constructed out of frames of these objects. And what is bundle, by the way, we will see probably already today, maybe. Just a small example. I will not delve into definition what is it, because we will not need it. It can wait 1 year, but we will see an example of this, what is a bundle. And now let's have a look at what are consequences for orbits that our action is free. So imagine that we have LG on M, which is free. Maybe not transitive. So we will just, the picture is that here is M with LG, here is some point, and here is orbit of this point M. Or we will call it that this is M, and this is some M0. We can go from the definition of what is orbit by some group element from M0 to M. Now we want to study whether that we know that from M0 to M we can go by LG, by definition. Yes, that it means that M is G M0, or in older notation LGM0. Now the question whether G is the only element which goes there. Maybe with some other G we also can go from M0 to M. Yes? So imagine that one of them is G, and we will call it G1, and another one is some G2, and imagine that we obtain equal result. So the picture is G1 does there, also G2 does the work. And what is the relation between G1 and G2 in general? So we can act on this equation by G1 minus 1. This is action. This is a point, and this is a point. And we act on these points by G1 to minus 1. Action by G1 and then action by G minus 1 is action by unit element, and it is nothing to do. So here we have M0 is G1 to minus 1 and G2 acting on M0 in general. Yes. Now, what does it mean? that this element, I will call it H, is from GM, 0, from stabilizer of this point M0. So there is a stabilizer of each point. Here is stabilizer of M0, it is some subgroup. Now we see that the relation between these two G's is that it should be some H from GM0, or G2 is G1 H, and H is from here. This is important result. That in general now, not for free action, but for general action, G is not unique element which goes from M0 to M. But there, in principle, there is a huge number of elements, some fixed one, some G1, and any G2 which is multiplication of G1 from the right by any element from the stabilizer of M0, from stabilizer of the original point. Yes? So if the stabilizer is a big subgroup, this is a big number of group elements which go from M0 to M. Now what happens when our action, we will go back to this result, it is important. What happens if our action is free? We know by definition that stabilizer is just unit element. So this H is just one guy, namely E, and it means that G2 equals G1. So there is a single element going from M0 to any other element of the orbit. What does it mean? That if here is M0, now if here is a unique G going to any M, that means that there is a bijection between the points of the orbit and the group elements. This is important. So if you want to know that how big is our orbit, we can answer it is exactly as big as the group. Yes? This is a bijection. There is a bijection of the orbit points and the points of the group. So somehow we can see the orbit. If we can see the group, in a sense that we know that this orbit is exactly like that. So for example, we want to visualize somehow this space. Because there is a free action of GL and R on these frames, all frames together look, so to speak, exactly like GL and R. Yes, there is a bijection between GL and R and the space of frames, because the action is free. Yes. Now, if the action is not free, if it is more complicated, that there is some non-trivial stabilizer, we see that there is bijection not of group elements and the orbit, but of some subset of group elements and the orbit, and we will study it in detail, that what is the situation there. There we have to introduce something like this object seriously, and it will be called a left coset, and we will study what are cosets and so on. Maybe it is good idea to do it just now. Okay, I will study it. I will start to do it right now. After this information, we will already better understand what is the role cosets. So definition of left coset. Imagine we have a subgroup, any subgroup of our group. Now we'll study a group itself with some properties of the group, without relation to any action now. And then we combine it. We will come back after understanding this. We go back to general actions and to have some relation. But now we studied something like independent study of some properties of any group. That study any subgroup of group. Then define this set. It is the set of all G primed from G such that G primed is given by GH and H is from the subgroup. So what is it? Actually, it is some orbit. It is quite useful to understand that we studied, it is some sidestep note, that how we can understand this, alternatively, that we know that there is action of G on G by right translation. K goes to KG, RG, right translation. So any group element can be used to multiply any other element, and we have an action which we already studied, and we know that it is a right action. Check, if you are interested, that this translation is free and transitive. So check. It is a good exercise for you to understand whether you understand what is free and transitive. Check that this right translation is free and transitive. But now, what we can think that we can, by this formula, we have also action of any subgroup on G. That simply put this G here from the subgroup. Yes, so if you have action of subgroup on your G by right translation, it has orbits, it is already not transitive, it is still free. Check that if you restrict to H on G. Yes, so K goes to KH only. Multiplication of two group elements. So it is still free and not transitive in general. So there are orbits, and the orbits are exactly as big as the group which acts, which is now H. Yes? So all orbits are in bijection with the group itself, because the action is free. We studied it here, that if action is free, you have bijection between group elements and elements of the orbit. Now, this action acts on group, so this is our M. There is some orbit, and the orbit is exactly as big as the group H, which acts. But now, what is an orbit? It is exactly this guy from definition. Because what is this? That take G as a start point. It is this K here. This G is K. So G goes to GH in other notation. So all GH for fixed G and arbitrary H from the subgroup. So it is exactly GH is an orbit of the point G for action of H on G by right translation. So what we see for this? First, that this H acts on G now. So G decomposes to orbits because there is some action. So G decomposes to orbits. We already know because there is some action of some group on this. Now, what we know, our action is free. So the orbits are as big as the group which acts, namely H. And that, but it is for any G. Yes, now, this is orbit of some particular G. And for any G, you have set of orbits for any G, it decomposes the group, but each orbit is of the same number of elements, so to speak, like number of elements of H. So there is a bijection. Bijection. And very useful picture to visualize all that, this concept of left cosets, is this one, that let this be our group G. You see that there are some corners. Do not take it seriously. It is symbolic picture. And here, let this be our H. There are some points of G. Here is another line, which is GH. It is this GH left coset. By the way, H itself is also left coset. For G equal E, yes, EH is H. So actually this is one left coset and this is another left coset, which is directly the subgroup itself. Now we know that there is a bijection, yes, so we can symbolically put it as mapping from this subset to this subset. And we see that the whole group decomposes to such lines here, symbolic lines, which are all possible left cosets. So the group is a union of its left cosets. And all left cosets are of the same big. Yes, there is bijection between them. So here is somewhere, because this is subgroup, somewhere here is unit element on this line. Unit element is always on the subgroup, or any subgroup. And here is somewhere G, because this line is GH. And what is GH? All elements of this type. So for H equal 0, equal E, there is always unit element in this subgroup. GE is directly G, so this is GE. And what is here? Here is some GH for some H non-zero. So here is G, and there are all other elements which are created by multiplying this G from the right by H. And for some G tilde, here you have somewhere G tilde, and here is G tilde H, and so on. So the whole group decomposes to left cosets. And all left cosets are bijectively mapping one to another. What does it mean for finite groups? Now, for us, the most interesting case will be Lie group. But this theory of actions and left cosets and so on, it also acts on any groups, including finite groups. So, for example, you have some group with 10 elements. And you think whether there is a 3-element subgroup there. If there is a 3-element subgroup, this H are just 3 points. Yes. Now, maybe there is, or there should be some other left cosets, because 3 is not equal to 10. So here is some other left coset, altogether 6. Here is some other left cosets, altogether 9. Here is some other, altogether 12. Too much. And what is the conclusion from this thinking? Just exactly here, that 10 cannot be created from several 3-copy elements. What is the conclusion? If we have group with 10 elements, what is the conclusion from this on this picture? Yes, that there is not 3-element subgroup, because it doesn't work. But, for example, if we have just two elements subgroups, it is possible, because 10 can be divided by 2. Yes? So you see that there is a simple fact that if you have some group with several elements, that the number of elements in any subgroup must divide the number of elements in the group itself. So if you have a 7-element group, which cannot be divided, hopefully, by other number than 1 and 7, there are no non-trivial subgroups of the group with 7 elements. Non-trivial means different than the whole group and the smallest group. This is connected with something called Lagrange theorem, or lemma. So maybe you had this fact on some lecture, that Lagrange theorem says something like that, which was explained, that there is some relation between the number of elements of the whole group and the number of elements or on any subgroup. Yes, that some subgroups are impossible simply by this fact. Now we can also think this relation that either to be in the subgroup or in general to be in a common left coset. Yes, this is this left coset generated by G. Now imagine we have two group elements in the same left coset. So this is some G hat. We can introduce equivalence relation that G is equivalent to G hat if G hat is G multiplied by H from subgroup. Check that this is an equivalence. Yes, so to be, this is an, actually it is a special case for we already had this, that if you are on M and you have 2 points which sit on the same orbit, you can treat it that they are equivalent in this sense, that to sit in common orbit is an equivalence. This is an orbit, so it is again equivalence. Yes. Now we can make now some set here, which is denoted as G over H, and it is called factorization, that factor space of this space with respect to this equivalence. So what is here? It is this set of points is now just one point in this space by definition. Put them all together, shrink them to a point, and introduce a new set for such points. It is here. It is called G over H. And it is called factor set of G with respect to this equivalence. So we factorize this set with respect to this equivalence, and here are equivalence classes. And these equivalence classes are denoted in mathematics by this symbol. That if here is G, then here is a one point, which is so equivalence class that all those are shrink to one point. And this class is denoted by H. From the definition of this class, we have that this class is the same class like GH class. Yes, here is GH, but it is at the same line. So it is equivalent to G, and then these two guys with these brackets, not without these brackets, but with these brackets as a class, it is the same class. So more or less, this is the definition of what is a class. Yes, the class is given by equivalence of G and GH. And now this picture altogether is an example of something which is called fiber bundle. I will not give exact definition. It is enough to give it in chapter 17 on the book, which is treated on this lecture in summer semester of next year. Official definition, what is fiber bundle, but something like that, that there are two sets, the bigger one typically and smaller one. There is a projection here, some mapping, that any element sitting in G here projects to its class. Yes, so this is given, pi is defined that G goes to its class. And it is clear that it is surjective mapping. This pi is mapping here from G to G over H. So this set maps somehow on this set down. There is surjective mapping that each element here has some element over it, which is projected to this class because the class was created from some elements. And what is inverse image? Inverse image of this guy is the whole line here. Inverse image are all elements which project to the single point. It is not, there does not exist inverse mapping to this. Inverse image is a subset. Yes. So inverse image of any point here is something which is called fiber. In the language of fiber bundles. Here, in our example, the inverse image is left coset. Yes, left coset is inverse image of this element. But in general theory of fiber bundles, these inverse images are called fibers. This is fiber over this element. So this subset is fiber over this, by definition. And what is important for fiber bundles, that all fiber bundles are like, that means there is a bijection between this fiber and this fiber. Any two fibers biject look the same, so to speak. Here, it is a fact that in our case, all left cosets look the same from the point of view of bijection, nothing else. So this G over H, we will specify to this space in a moment today. Oh, to 40, yes, still 5 minutes, okay. Okay, so we will, for us, this will be very interesting set now. And why it is so interesting? So it is an example of fiber bundle, which is not important now, but if you hear sometimes something about fiber bundle, there is something denoted or described by this picture in general, yes? This kind of picture. Now, why this G over H is interesting? Because it is a homogeneous space for group G. So what does it mean? That this group acts here. There is some left action on elements. So this is from G over H, and this G is from G. So this group acts on, or I can show it here, that this element acts on this point, on the set of these points. It acts down. Yes? Any element from G acts on this set. And what is the formula? It is GK bracket. So how it works? I will use a new picture because it is already somehow too much there. So here is G as a group. Here is an element. Here is G over H, and somewhere here is a K. What does it mean? That over it somewhere is the element K. This is the class K. And what is said here? That you want the action of this element on this element, then do it in this way. Act first by this element on this element, this K, it is here, by left translation. This is left translation of this on this. And then you obtain something by multiplying this and this, you come here, for example. Here is some fiber, go down, and here is the result. This says this formula. That, or in other words, this K here is a representative of this class. There are many representatives. One of them is this K actual. Other representatives are KH, yes, for any H. But take this K, act on it by G, by multiplication. Here you have result. Here is what? Here is GK as an element. And here somewhere is GK as a class. So you come from K class to GK class by this action. Now, do you feel some danger in this definition? That perhaps it is not very good definition? In which case it will be bad definition. We used one representative of this class. The danger is that if you use other representative of the same class, we will obtain something else. So if this definition depended on the choice of the representative, it will be bad definition. So we want to show that what happens if we act in on other representative, which is always some kh. For arbitrary h from the subgroup, they are all representatives of the class K. Yes? So what happens? By definition, it is apply G from the left to this element. So it is G applied to KH and then taking class. But it can be written as GKH because of the property of group multiplication, associativity. And what does it mean now? Then it is the same thing like GK because H on the right-hand side is not important in the class. Yes, whenever you see this with some H on the right-hand side, you can cancel it. So we cancel this H. What we see that this is well defined. In spite of the fact that it is defined through representative, it doesn't depend on the representative. So it is okay definition. And now what is interesting? That this action is transitive proof, simple proof, that this action, first of all, is well defined, and second, it has nice property that it is transitive. What does it mean? That this space is homogeneous space. This is just one orbit. So we have nice example of construction of homogeneous spaces. This will be the last part of my lecture, that whenever you have a subset of your group, your group acts on G of G over H, which is some very well-defined object, in such a way, here is the way, which gives you from G over H a homogeneous space. So you have now a factory for construction of homogeneous spaces. You want homogeneous space for group G. Find any subgroup, construct G over H, and you have homogeneous space. And next week, we will show that those homogeneous spaces constructed in this way are actually all homogeneous spaces existed for group G. There are no other homogeneous spaces in some precise sense. What does it mean? Then this construction. This construction gives you all possibilities of homogeneous spaces for your group G. This is the reason why this construction is so important, that there are no other homogeneous spaces. We will show it next time.